Okay, this is a review of acids, bases, and salts in preparation for this week's unit exam. The behavior of many acids and bases can be explained by the Arrhenius theory. The Arrhenius theory of acids and bases basically is that they are electrolytes. An electrolyte is a substance which, when dissolved in water, forms a solution capable of conducting an electric current. The ability of a solution to conduct an electric current depends on the concentration of ions. So acids, bases, and salts are all electrolytes because they dissociate. For example, HCl will dissociate into H plus and Cl minus. So if I have HCl, it dissociates into H plus and Cl minus. I now have charged ions. If I have NaOH, it will dissociate into Na plus and OH minus. I now have charged ions. And if I have NaNO3, which is basically a salt, it will dissociate into Na plus and NO3 minus. As long as I have ions in solution, I have the ability to conduct electricity. Properties of acids and bases. Well, they both dissolve in water. They are both electrolytes. Acids taste sour, like lemon juice, while bases taste bitter. Acids neutralize bases, and bases neutralize acids. Acids react with active metals to form hydrogen gas. Bases emulsify fats and oils, meaning it's what our dish detergent is made up of, our laundry soap, our shampoo. They also feel very slippery. And you know, if you've ever used shampoo or a cleaner or dish soap, it kind of does feel slippery. Acids have a pH less than 7, while bases have a pH greater than 7. Acids turn blue litmus red, and bases turn red litmus blue. So which species can conduct an electric current? Mind you, I am looking for an acid, base, or salt. Well, here's my metal and an OH. We know that's a base. This is not a base, even though it has OH, because this is not a metal. This is water. We know it's neutral. And this is HCl, and that's an acid. So upon first inspection, you think that you might have two answers. However, this NaOH is solid. Solids don't conduct. They need to be aqueous. So choice 4 is our answer. And those are basically the same things that I told you. NaOH would conduct, but it is a solid. It's not dissolved in water. CH3 is an alcohol. Water is a non-electrolyte. HCl is the only electrolyte. Which 0.1 molar solution contains an electrolyte? This one's tricky because you know that you're looking for an acid, base, or salt. However, I briefly told you that acids start with H plus, or they can end in COOH. And this is indicative of an organic acid. So here they were trying to fool you. Arrhenius acids yield H plus hydrogen ion as the only positive ion in an aqueous solution. The hydrogen ion may also be written as H3O, hydronium. An Arrhenius acid has. Hopefully you chose number 3, hydrogen ions as the only positive ion in solution. Which substance is an Arrhenius acid? Remember, you're looking for a compound that will dissociate to produce H+. Good, you chose number 2. Table K lists the names of some common acids. Please don't forget about it. It could be very useful during the test or the Regents exam. An organic chemist would write the formula for acetic acid this way, as you see here. However, most of the time when I write it as HC2H3O2, so that you can see that the H is right out in front and it is an acid, but they are the same compound. Arrhenius bases yield OH minus hydroxide ion as the only negative ion in solution. So which ion is produced when an Arrhenius base is dissolved in water? I know, since I just reviewed it, that you all chose number 3. Table L lists the names of common bases. Notice how they are all a group 1 or group 2 metal with the OH ending. With the exception, of course, ammonia, which we've talked about, is considered a weak base. It is a base, but it is not an Arrhenius base. Ammonia is a base when it dissolves in water. It produces hydroxide ions. You can see here that water acts as an acid because it donates H to NH3, and NH3 is the base because it accepts it. I'm going to review a little bit right now because remember, conjugate acid-base pairs only differ by H. So if this is the acid, then this is the conjugate base. If this is the base, then this NH4 plus is the conjugate acid. In the process of neutralization, an Arrhenius acid and an Arrhenius base react to form a salt and water. So here you have an acid plus a base yields salt and water. The salt that's produced depends on the nature of the reactants, but water is always a constant. You need to be able to complete neutralization reactions and balance them. The nonmetal from the acid, which is the plus, combines with the metal from the base, which is the negative, to make the salt. So the positive Na and the negative Cl combine to make salt. The H from the acid combines with the OH from the base to make water. Given the reaction is best described as. Now, if double replacement were a choice here, you could certainly choose that because it is a type of double replacement reaction. But more specifically, we have an acid due to the H and a base due to the metal and the OH producing water and a salt. So our answer is neutralization. Which equation represents neutralization? Hopefully you chose number 4, an acid and a base, because it yields salt and water. Titration is a laboratory process in which a volume of solution of known concentration is used to determine the concentration of another solution. MAVA equals MBVB, where MA is the molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. At the equivalence point, the moles of H are equal to the moles of OH. In this problem, when 50 milliliters of an HNO3 solution, so this is our VA, is exactly neutralized by 150 milliliters of, here's my linking words, of KOH, so that's base. So this is my VB and this is my MB. What is the concentration of HNO3? So we're looking for MA. So let's plug in what I have. I don't have MA. I have my VA, which is 50, and that's going to be equal to my MB, which is 0.50, times my milliliters, 150. So I've got 0.5 times 150 divided by 50 to get my X, and I get X equal to 1.5, which is the molarity of my acid. So my answer is 2. If 5 milliliters of a 0.2 HCl solution, so this is my MV, this is my MA, is required to neutralize exactly 10 milliliters, so this is my VB, what is the concentration of the base? So I don't know my MB, that's my question. So MAVA equals MBVB, so I've got 5 mils, and I've got 0.2 molar equal to X times 10. So I've got 0.2 times 5 divided by 10, and I get an X of, okay, so I get MB equal to 0.1 molar. And that is my answer. A titration setup was used to determine the unknown molar concentration of a solution of NaOH. A 1.2 molar HCl solution was used. So right away I know that this is my MA. The following data was collected. So at trial 1, well, for all trials we use 10 mils. So there's my VA. I know that we use 10 mils for all trials. And then they give me the initial burette reading and the final burette reading. So remember, the burette is that thin device that we put the base in, and it's got, comes down to like a little point, and you can turn it on and off, and it has all these increments on it that you can read. So let's say my base was up here and then it went down to here. That's what they're showing you. The initial volume was this, the final was this. So in order to find the actual volume used in each trial, we would have to subtract. So it says calculate the volume of NaOH used to neutralize 10 mils of the standard HCl in trial 3. So we're interested in trial 3. So our initial was 23.2 and it went down to 35.2. So if we subtract, we will have our difference. So 12 milliliters of NaOH was used in trial 3. Where is it? And that's what they did. According to reference table M, what indicator would be most appropriate in determining the endpoint of this titration? Give one good reasoning for choosing the indicator. Well, if you go to table M, a good one to use for an acid-base titration would be phenolphthalein. You can also use bromthymol blue because it does change color at a pH of 7. But phenolphthalein is always a good choice for titration. Calculate the average molarity of the unknown NaOH solution for all 4 trials. Your answer must include the correct number of significant figures and correct units. So, the easiest way to do this is MAVA equals MBVB. Notice that the molarity, which we got in our first reading, 1.2 molar, is the same in all. Our volume is also the same in all, 10. We have to figure out the difference. So you can see here in trial 1, 12.2 minus 0 is 12.2. Then 23.2 minus 12.2 is 11. In trial 2, we already figured trial 3 was 12. And in the last one, 47.7 minus 35.2 was 12.5. They got all the molarities, all 4, added them up, and divided by 4. There are alternate acid-base theories. One theory states that an acid is an H plus donor and a base is an H plus acceptor. I want to be clear that I call this the Bronsted-Lowry theory of acids and bases. The Regents used to also call it the Bronsted-Lowry theory of acids and bases. In the last couple of years, they have referred to this as the alternate acid-base theory. So when they're talking about Arrhenius theory of acids and bases, you will know it because they will use the word Arrhenius. They may or may not use the Bronsted-Lowry theory of acid and bases. They may refer to it as the alternate one, you know, like the other acid-base theory, but they're really talking about Bronsted-Lowry. So in this case, HCl is the acid because it donated an H to NH3, which is the base. And then my Cl minus would be my conjugate base, and my NH4 plus would be my conjugate acid. The acidity or alkalinity of a solution can be measured by its pH value. The relative level of a solution can be shown by using indicators. Red litmus turns blue in a base, and blue litmus turns red in acid. You can also look at Table M. Remember that the left number gives you the one extreme, the right number gives you the other extreme, and in the middle it's a blend of colors. So 3.2 or less, it would be red, 4.4 or greater, it would be yellow, and in the middle here, greater than 3.2 but less than 4.4 would be probably orange, because that's a blend of red and yellow. When the pH is lower than the lower number in the range, the color is the color on the left, which is what I just told you. When the pH is in the higher than the higher number in the range, the color is in the color on the right. And when the pH is between the two numbers, the color is changing and is probably somewhere in the middle. A compound whose water solution conducts electricity and turns phenolphthalein pink is what? Well, phenolphthalein pink is a base. Phenolphthalein clear is an acid. So we're looking for a base here, so our only possible choice could be 3. A student was given 4 unknown solutions. Each solution was checked for conductivity and tested with phenolphthalein. The results are shown in the data table. So we know that A and B are acids, and we know that C and D are bases. Based on the data table, which unknown solution could be 0.1 molar NaOH? Well, we know that it's going to be C or D because it's a base and phenolphthalein is pink. But is it going to be a poor conductor or a good conductor? Well, we know that group 1 and group 2 bases are strong bases and they 100% dissociate. So it would be a good conductor, choice C. A student is given 2 beakers, each containing an equal amount of clear odorless liquid. One solution is acidic and the other is basic. Say 2 safe methods for distinguishing the acid solution from the base solution. So this type of question, they're asking you to use maybe indicators because they're telling you one is acidic and basic. So phenolphthalein is a good choice. Litmus paper would be a good choice. A pH meter would be a good choice. Any of those. For each method, state the results of both the testing of the acid and the base. So if we tested it with litmus paper, for an acid, blue litmus would turn red, and for a base, red litmus would turn blue. For a pH meter, for an acid, the pH would be less than 7. For a base, it would be greater than 7. If we used phenolphthalein, for an acid, phenolphthalein would be clear, and for a base, it would be pink. On the pH scale, each decrease of 1 unit of pH represents a 10-fold increase in hydronium ion concentration, H3O+. So, in looking at this pH scale, remember that when I go more towards 1, this is my strong acids, way down here near 0. And this is my strong bases, way up here near 14. An acid with a pH of 2 has 10 times the hydronium ion concentration as an acid with a pH of 3. So it's 10 times more when I go from 3 to 2. It's 10 times less when I go from 3 to 4. A base with a pH of 10 has 100 times the hydronium concentration as a base with a pH of 12. So when I go from 12 to 10, the hydronium ion concentration increases 100 times. When I go from 12 to 14, it decreases 100 times. pH is the negative of the power of 10 of the hydrogen molar concentration. A pH of 7 simply means 10 to the negative 7 molar, H plus for pure water. So if I told you that the concentration was 1 times 10 to the negative 7, you could simply take the negative log of that and you would get a pH of 7. For purposes of this class, honestly, you can look at the exponent and it will give you the pH. So if I say 1 times 10 to the minus 3, that's really a pH equal to 3. Here's some relative pH values of some common substances. You can see stomach acid is around a pH of 3. Coffee is slightly acidic at a pH of 5. You can see that blood is slightly basic. Oven cleaner really bad stuff, pH of 13. Which of these 1 molar solutions will have the highest pH? Highest pH. That means closer to 14, so I'm looking for a base. NaCl is a salt. It's a metal and a halogen. HCl is an acid. It begins with H. CH3OH is an alcohol, which I didn't teach you that yet, but it's certainly not a base because it's not a metal and OH. So the only one that's a base is number 1. This just shows you the chart of pH and the hydrogen ion concentration. So as I was telling you before, 1 times 10 to the minus 3 is a pH of 3. 1 times 10 to the minus 10 is simply a pH of 10. 1 times 10 to the minus 13 is a pH of 13. 4 flasks each contain 100 mils of aqueous solutions of equal concentrations. Which solutions contain electrolytes? So, if it's an electrolyte, I'm looking for an acid, base, or salt. Well, let's look what we have here. KCl is what? It's a metal and a halogen. This is a salt. CH3OH we don't have to know that it's an alcohol. We just have to know that it's not a base because it's not a metal and OH. This is a base. There's my metal and OH. And this is an acid, not because it starts with H, but because it ends in COOH, which is an organic acid. So, which contain electrolytes? Well, that would be KCl, BaOH2, and CH3COOH, all three. Which has the lowest pH, meaning which is most acidic? That would be the CH3COOH. What causes some aqueous solutions to have a low pH? Well, if something has a low pH, then they are acids. They have dissolved hydrogen ions. Which solution is most likely to react with an acid to form a salt and water? Well, to form a salt and water, I need a base and an acid, and I already have the acid, so that means I'm missing the base, the BaOH2.